Okay. Good afternoon, everyone. Am I audible?
Yes,
Okay. So today is the sixth interaction session on reliability-based structural design. So this course is instructed by Professor Arunasis Chakraborty, IIT Guwahati. My name is Devashish Panda. I am a research scholar and Prime Minister Research Fellow at IIT Guwahati, and I have been allocated to this course as a PMRFTA. So every Sunday, sorry, from 3 to 5 p.m. we meet and we discuss the current topics and we solve the problems regarding that current week assignments and all these things. So today we will go through the iso-probabilistic transformations. So first we will go through the Morgenstern and Nataf model. We will solve problems and verify them using MATLAB. You know, these models will give us the bivariate or multivariate distributions. So we will check whether these distributions are, uh, align with the prescribed marginals or not. Then we will move to Rosenblatt transformation and we will solve problems. Okay, so let's quickly start. So, before going to that iso-probabilistic transformations, let's quickly revisit that concept of, the joint distribution or the multivariate distributions. So, if we have recall, we already have discussed these things during the first interaction session, though we need to revisit so that the concept of that iso-probabilistic transformation, why we need them, that thing will get clear. So recall that if we have two random variables x and y, and if their joint PDF is defined by f of xy given xy, then we can easily find it out. The probabilities lies between one interval between x and one interval between y. We can directly integrate within that intervals and get the probability value. And also we know that the volume under this joint PDF will be 1, and if we have the PDF we can get the CDF, and if we have the joint CDF we can get the PDF. So these were the properties of the joint distribution or multivariate distribution. If we have more than one random variables, so how we can define their joint PDFs and CDFs. So these are the properties. Now if we have some joint PDF, okay, for say for example we have two random variables here x and y, and we have plot this joint PDF like f x y given for some values of xy, so we get this curve. Now if we have the joint distribution and if we integrate over one domain, we will get the marginal of other. Like the marginal distribution of x, that means if x given x, we can easily find it out from the joint distribution. How? We just need to integrate within that domain over the other, other random variable, that other domain. If we integrate them, then we can find out the marginal. Similarly, we can get the marginals of y, like if y of y will be nothing but we need to integrate it. Say for example, this is nothing but a normal distributions. That's why I'm considering the domain as minus infinity to plus infinity f xy of xy and dx. So if we have the joint distribution, we can get the marginals, by integrating over the other dimension. So if we integrate this over dy domain, so we will find out the marginal of x. Similarly, marginal of y, we can find it out if we integrate it over the another domain. Now the thing is, if we have the joint distribution or multivariate distribution, we can have the marginals. Now if we have the marginals, can we get the joint distribution back? Okay, this is the first problem statement. Like in engineering applications, most of the time, like we can for a data set we can prescribe, okay, for this data set we can go with that marginal. Okay, for example, log normal, normal, or exponential. These are the marginal. Now very often we need that bivariate or multivariate models. These are not readily available. So the problem statement here is how we can construct the joint distributions from the marginals. Like if we have normal distribution, so from the marginal of normal distribution we can construct the joint distribution of normal. But for the normal case, here we can see if we have k dimensional marginal distributions, we can construct the joint distribution of this. And the if we plot the joint distribution over two dimension x1 and x2, and this will look like this. So for the normal distribution, we can easily get the joint distributions from the marginals. But for the other cases, if we have different kind of distributions like log normal, normal, Gumbel, or different kind of, we have studied and we have you know uh, we have went through that our limit state may contain different kind of random variables and different kind of correlation coefficient may be there. So to establish that two things, like from marginals how we can get that uh, joint distribution or multivariate distributions, first thing, and how we can define that correlations of this that the two distributions. Okay, so recall that we have different kind of distribution in marginal forms, like already we have seen, like uniform distribution. For this uniform distribution, this is the PDF, probability density function, and this is your the parameters. So these all things we already know for the marginals. Now here the problem statement is clear. From the marginals how we can get the joint distribution, and this joint distributions or the bivariate distribution should be consistent with that prescribed you know marginals. So this is the main problem statement for our iso-probabilistic transformation. Now for this we have actually two models, Morgenstern and Nataf. And these two models are taken from this paper, or first proposed in this paper, multivariate distribution model with prescribed marginal and covariance. So I will show you the paper, because today's discussion will be based on the findings of this paper. Whatever they have listed, we will go with them. So if I quickly share this paper with you, just I show you some glimpse of the paper, then we will come back uh, to this PPT. Okay, so for example, if we have this, so here you can see, one second. Okay, so I hope this paper is now visible to you, right? So this is the actual paper from where we have taken this model, Morgenstern and Nataf, and we will discuss one by one. So all these things are described in this paper thoroughly. So if you go through it, you can find out, look, the Morgenstern model, uh, and if you go below it, so you can find out the Nataf model along with different kind of examples already they have given here. So these all things, all tables, all the parameters we have taken from this paper. So I will share this publication with you once the interaction is completed. So let's go back to our PPT and let's see that how this Morgenstern and Nataf model will work, and through them or with them what we can actually do. Okay, so the problem statement, I hope the problem statement is clear. Like, if we want to construct the bivariate or multivariate distributions from the marginals, how we can do them, and also we need to verify that whatever uh, the bivariate or multivariate distributions we are getting, that should be consistent with the prescribed marginals. Okay, so first we will go through the Morgenstern model, whatever they have prescribed in that paper. Okay, so first, for the Morgenstern model, if we have, like, first we will talk about the bivariate distributions. That means we have only two random variables. So for example, if we have x1 and x2, two random variables with their marginal CDFs are given, like for x1 the CDF, that means cumulative distribution function, if x1 of x1 and if x2 of x2 are given. Now, if I have these two marginals of these two random variables, so what will be the bivariate CDF? That means the joint CDF for this. So this is the expression they have proposed. Like this will be that your bivariate CDF will be nothing but, fx of x1, that means the marginal CDF of x1 multiplied by marginal CDF of x2, bracket 1 plus, you know this is actually the parameter what we are looking for. That means alpha 1 minus the CDF of x1, 1 minus CDF of x2. Look at this expression. This will give you the bivariate CDF of these two marginals. Now here we can see that within that expression we know the f x of x1 and f x of x2, that means two CDFs. Now our goal is to find out this alpha. What is that alpha? That is nothing but a scalar factor that will depend upon different kind of nature of random variables and the correlation coefficient. So we will see how we can find out this value of alpha within a minute. So this one will be the expression for the bivariate CDF, and simultaneously we know the relation between CDF and PDF, right? So once we have the CDF, we can easily construct the PDF. PDF will nothing but, we need to differentiate the CDF with respect to x1 and x2. So this will be the expression for the PDF using Morgenstern model. So this is nothing but the bivariate PDF, that means the joint PDF. So we have the expression of the Morgenstern model. If we have two random variable, how we can construct the joint CDF and PDF. Till now, one parameter is missing, that is the alpha value. Now, for the Morgenstern model, there are some limitations like the joint PDF, that means if x1 and x2 should be greater than 0, and this actually requirement will lead to that alpha mod of alpha, that scalar value should be less than equals to 1. So this thing we need to keep in mind, like we along with this expression we can find out the range of different correlation coefficient on which or on the range the Morgenstern model will valid. Okay. So how we can get this? So from the they have established, like from the relation of correlation coefficient. What is the definition of correlation coefficient? Rho is nothing but covariance between, say, rho of x1 and x2. If we need to find it out, so that will be nothing but covariance of x1 and x2 divided by sigma x1 and sigma x2. So this is the relation of the you know correlation coefficient. Now, if we simplify this expression, and actually they have simplified this expression and given a handy and compact form to calculate the value of alpha. So alpha will be nothing but rho 1 2, that means the correlation between that two random variable divided by 4 q1 and q2. So I will give you, or I will describe you what will be the generic form of this once we will complete with that two random variables. Okay, for if we have n number of random variables, what will be the closed form of alpha, or the closed form solution for the alpha? So here we can see that rho 1 2, the correlation between two random variables, that we can have it before any solution. Our task is to find out the q1 and q2. Now, to find out the q, the expression for q is nothing but this: minus infinity to infinity xi mu xi by sigma xi multiplied by marginal PDF multiplied by marginal CDF. Now, this thing, if we have, for example, we have, say, we have log normal distribution. So log normal distribution have two parameters. If we can find out these two parameters, we can numerically solve the q. Now the thing is, for their work, like numerically, when we want to solve it, say for example, numerically it will take more time. It will be, like when we will solve some reliability problem, so it will cost more time, right? So they have given some values, or they have prescribed in their paper, in this paper they have prescribed values of q1 q2 directly, values of q1 q2 based on the nature of the distribution, or we can say based on the nature of the marginals. Okay, so first what they have done, right, to find out that q1 q2 value, they have categorized the random variables into two groups. First group, group 1, what they have said that these random variables, we can reduce them to their standard form, like normal. In group 1, the normal distribution, uniform distribution, exponential and shifted exponential, Rayleigh, type 1 largest and type 1 smallest, they will fall under this group. So they have categorized this. Okay, so this distribution will follow under group 1, and these distributions like log normal, gamma, type 2 largest and type 3 smallest, these are under group 2 distribution. And as per the groups, they have solved the equation and prescribed these values for the q1 and q2. So for group 1, so for example, if we have normal distribution, so the value of q will be 0.282. And likewise, for the other distribution of type 1, we can have the value. So here we can see that for group 1 distributions, the values of qi are the constant values, while on the other hand, if we look into the group 2 distribution, here we can see the q values depends on the parameter of the distribution, or more precisely we can say the shape parameter of the distributions. Okay, so from these two tables, if we have, or if we know the marginal distribution, we can find it out q1 and q2. And once we can find it out q1 and q2, we can find out the value of alpha. Now once we can have the alpha value, we can easily construct the JPDF or the JCDF using the Morgenstern model, using this equation, right? Okay, so this thing will get more clear when we will solve one example. So first thing, what Morgenstern model does, it gives us the bivariate or multivariate distributions based on the marginals, and these distributions are you know uh, consistent with the prescribed marginals. So we will check and verify within a minute, like what they have said, this actually follows or not. So for example, let's go deep into it. Like what I said, for Morgenstern model, we have some limitations, like our JPDF should be greater than equals to 1, and that criteria will lead to that our that alpha value, the scalar value, should be less than equals to 1. Now this is very important relation. From this relation we can find it out, like in which range of correlation coefficient between two random variables this Morgenstern model will validate or will valid. So let's say, for example, we have x1 and x2, two marginal normal distributions. We have one, x1 is marginal normal, x2 is uniform. So if we want to know that, we have two distributions, we know these two distributions will fall under which group. Now one question still remain. For like if I say the correlation coefficient between x1 and x2 is equals to 0.2, and for one case, for the same random variable, I said that x1 and x2, the correlation coefficient between 0.7. Now for 0.2 and for 0.7 correlation coefficient between two random variables, the question is the Morgenstern model is valid for these two cases? So we need to find out the maximum values of correlation coefficient on which or within which the Morgenstern model will be valid. Because recall that Q1 and Qi formula we have basically derived based on the correlation coefficient. So here we can see that we have two random variable x1 and x2. So when we know that x1 fall under normal distribution, x2 fall under uniform distribution, we can find out the q1, q2. So what will be the value of q1 and q2? Here for normal distribution 282, and for a uniform distribution 0.289. So now if we put these values here, so What was our equation? That alpha, this is our criteria, should be less than equals to 1. Now alpha is equals to what we know. They have given the formula for this, rho 1 2 divided by 4 q1 q2 should be less than equals to 1. So here we can have that, okay, q1 q2 value should be less than equals to 0.326. That means the correlation coefficient, if we have between two random variables, the correlation coefficient above that 3 to 6 for this normal and uniform distribution, so we cannot apply the Morgenstern model. So there are some limitations. Okay, we need to check for the correlation coefficient up to which this model will work. Then we can go with this model. So here in this paper, they have, found out the correlation coefficient or the range of correlation coefficient between different random variable, like for normal, for normal uniform, and all these things you can see for group 1 and for group 2. And we can see that maximum value is like 0.333, above which this model will not work. So we will discuss, how we can ultimately counteract these limitations. So up to that limit, if that satisfied, we can get our bivariate and multivariate distributions from the Morgenstern model itself. So let's quickly solve one problem. Then this thing will get more clear. Like,
Hello.
yeah, Bob.
The subscripts on the at the top, the SE and those things. Where are they defined?
That normal and standard, that exponential, these things.
Yes, where are they defined?
Like these are marginals. Marginals, you have already know what is the normal distribution, what is the exponential distribution, and as per this paper, they have categorized into these two groups. These are listed on the paper. I have just shown the
Okay,
paper, this paper. I will share with you this paper. This entire
okay.
PPT, the these tables and all these things, we are getting this from this paper.
No, no, no. I'm clear. Thank you. I'm clear. Thank you.
Okay, so I will share it with you. No problem. Okay, this.
All right. Thank you.
And they numerically solve this problem and prescribe these values. And this paper actually published in 1986. So these are the basic of these models. Okay, great. Okay, so let's quickly solve this problem, so this thing will get more clear. So let, for example, we have two random variables x1 and x2, and which are, first one is marginally normal. That means it has two parameters, mean and sigma. The two parameters are given. And the second one is exponential. Exponential distribution have only one parameter, that is lambda, right? Recall the distribution of the exponential distribution. Minus lambda e to the power minus lambda x. Now the correlation coefficient is given between that two is -2. Find out the joint distributions using Morgenstern model. So recall, if I need to find out the joint PDF using Morgenstern model, this is our equation, where we need to find out this alpha value first. Because for normal distribution, we know what will be the marginal of normal distribution. That means fx of x, this one will be 1 x1. And what will be the fx of x2? Simultaneously, we can get the CDF also, because this value PDF and CDF for the marginal, normal, and exponential distribution, we can get it. But first thing, we need to find out the alpha value. So to get the alpha, we have this closed form equation, that alpha is equals to rho 1 2 divided by 4 q1 and q2. So rho 1 2 we know, already given, minus 0.2. What do we need to find it out? We need to find it out q1 and q2. So here, how we can find it out q1 and q2? Already these values are prescribed in this table. So let's see what will be the values of q1 and q2. For normal distribution, it is given like this, and for exponential distribution also it is prescribed here. So from here, from this table of group 1 distributions, we can get them directly. So let's check. Yeah, so 282 and 0.25. Now if you solve it, So you will get alpha is equals to nothing but 0.7092. Now, once we have the alpha, can we construct the joint PDF using the Morgenstern model? Yes. Because for normal distribution, we know what is the PDF of normal distribution. This one is the PDF for the normal distribution. We all know, we have seen many times what is the PDF for normal distribution. 1 by sigma x1 under root of root pi e to the power minus half x1 minus mu x1 by sigma x1 whole square. So this one is your fx of x1. That means the marginal of the or marginal PDF of the normal distribution. Now we have exponential distribution for x2. So this one is the fx of x2. That means the PDF of the exponential distribution. What was the PDF of the exponential distribution? Lambda e to the power minus lambda x. Great. Now simultaneously you put these values here. So this is nothing but the CDF of the normal distribution, and this is nothing but your CDF of the normal distribution. Sorry, exponential distribution. So if we simplify this equation, like for our calculation purpose, we will get that fx of x1 x2, that means the joint distribution, we just separate it out, first part and second part, h1 and h2. So first part we can write like this and second part we can write this. So this is actually the bivariate PDF of these two random variables using Morgenstern model. Now if we plot this PDF over some values of x1 and x2, say for example x1 and x2, if we plot them, we will get this curve. So this is nothing but your joint PDF of these two random variables. Simultaneously, we have the equation for the joint CDF. We can, if we plot it, we get this as joint CDF. We will plot in a minute in a MATLAB these things, how from where we are getting this and how to plot them we will see. So now we have the multivariate model, or precisely for this example bivariate model. Now the thing is the model is correct? Is the model is consistent with the prescribed marginals? So how we can check it? We get the JPDF and JCDF. Now we can work with that JPDF and JCDF for these two random variables. But the question is my JPDF and JCDF, whatever I have calculated using or whatever I get from the Morgenstern model, are they consistent with the prescribed marginals or not? That is the main question. So how we can verify them? How we can verify this statement? So we have JPDF, that means if x1 x2 of x1 x2. Now from here, if I want to get the marginals of x1, if x1 of x1, how we can get it? How we can get it? Tell me. If I want to get the marginals from this JPDF, how we can get it? We have already discussed that we can have the marginals from JPDF or JCDF. So marginals,
by by integrating it around along one of the.
yeah, other dimension. That
Yeah.
means we need to integrate it over the x2 dimension, right? So here the x2 dimension is for exponential distribution. So 0 to infinity, we need to just x1 x2 of x1 x2 and dx2. So we'll get the fx1, the marginal from this JPDF. Okay, and x1 is the normal marginal that we have already considered. So this one is we are getting from the constructed JPDF. Now can we plot the actual marginal? This is the actual marginal of the normal distribution, yes or no? If we have two parameter of normal distribution, mean and sigma, can we plot the marginal? Can we have the marginal f x of x? Yes.
Yeah.
So there is only one way to check them. Plot these two marginals. If these two marginals are same, equal, then we can say okay, my JPDF is consistent with the prescribed marginals. So here I have first this red line. If you see this plot, this one is for uh, x1, the marginal of x1, that means f x1 of x1. So From Morgenstern model, we get this JPDF. If we integrate it over x2, we will get the marginal of x1. And this yellow plot, precisely this yellow plot will give you that marginal, right? Now, I need to plot the actual marginal fx of x1, right? So fx of x1, how I can plot? Using the actual value and using the actual distribution. And we can see that the two PDFs are actually overlapped with each other. That means our model is okay. Now for the second random variable, again for the second random variable, we can construct the actual marginal from its parameter. It's an exponential distribution with mean 1. So mean 1, that means for mean we can find out the lambda is equals to 1 by mean. Then we can plot it and we can have this yellow curve if we integrate the joint PDF over x2, and we have seen that two plots overlap with each other. That means our joint distribution model are consistent with the prescribed marginals. So we can conclude it. We will see, we will plot them in a minute in MATLAB. Then this curves will, from where I am getting this curve, this will get more clear. So is it clear from your end what actually the Morgenstern model do or does? Yes or no?
Yes.
Okay. So let's quickly solve another problem, then we will go to the MATLAB and plot these things, all these things. Okay. Now this, let's say we have two, again we have two random variables. So here still we are at the bivariate level, then we will go for the multivariate one. Okay. So let's say we have x1 and x2, two random variables. One is log normal. The parameters are given. These are the parameters for the prescribed marginals on which, based on which you need to construct the JPDF or CDF. And type 1 smallest. And the parameters are given for the type 1 smallest. Now, log normal, normal, type 1 smallest, uniform, Gumbel. For this, if you want to know the distributions and their respective parameters, so you can refer to these two tables what I have added, and these two tables are taken from these books. You can get it. Like the distributions are given, look, and corresponding parameters. You need to know about the parameters. Otherwise, you cannot construct or you cannot use the PDF properly. Yes. So you know for random normal random variable, you know that are two parameters. Log normal variables two parameters. Exponential have one parameters. Which are the parameters? How we can get these parameters? So you can have from here, or you can recall them, some of them. Okay. Now let's move to our problem statement. Yeah. So first we have log normal and type 1 smallest. So log normal have two, you know, parameters. So let's first quickly get these two parameters, because we will plot these actual marginals too. So we need to find it out too. So log normal, first we need to find it out the coefficient of variation. This is one of the parameter for the log normal distribution. So the coefficient of variation del is nothing but the sigma by mu. So sigma and mu values are provided, sigma and mu. So we can get the value. Now sigma ln z, this formula already given, say ln del x1 square plus 1 and x tilde. So these two are the actual parameters for the marginal log normal distributions. Similarly, for the type 1 distribution, it has two parameter u and alpha, and they are depend on these values like mu and sigma. So we can find it out u. The formula is given on the table. Go and look at the table how we can find out the u for the type 1 smallest distribution. It's nothing but mu1 2 plus some values divided by alpha. So first we need to calculate the alpha, and alpha we are getting from the sigma value. So here you can get these parameters for this. So for your reference, I just quickly show you that. Like what over our type 1? Yes, type 1 smallest. You can see it here that u and alpha. These are the two parameters. So you can either get it from here or you can recall them also. So once we have these two parameters, now focus on it. Once we have two parameters, now we can find out the q1 and q2 value. So first we need to find out the q1. Now tell me how we can find out the q1 value quickly. Either we can numerically solve using that row ij formula, or directly go to the table whatever they have prescribed. And we have seen that their model are well aligned with the marginals. So we have no issue with that. So log normal case and type 1 smallest. So let's see. Say log normal, it's fall under group 2 here for the log normal. So for the log normal case, we need to actually calculate the Q1 based on this formula. What this formula says, the 2 phi, that means standard normal variate of sigma ln x under root of 2 and this. So already we have calculated sigma ln x. Okay. And we have type 1 smallest. For the type 1 smallest, we can get the values directly from here. Clear? So we get these two values. Now we can easily calculate the or construct the alpha here. So for type 1 smallest, it will give the direct value. And for Q1, that means the log normal case, it falls under the group 1. So group 1, Q1 value, this formula, just we have seen it. Now equate or put the value of sigma ln x. Sigma ln x already we have calculated this. And if you simplify it, you will get the value as 0.2764. Okay. Now we can calculate the alpha value. Now once we have the alpha value, now we have the equations to construct the JPDF. So this one is the equation for JPDF using Morgenstern model. So fx of x1, this one will be 1. Okay, make it correct. Fx2 of x2 plus 1 plus alpha 2f of x1 and 1 minus 2f of x2. Now first distribution is log normal distribution. So fx of x1 we need to put for the log normal distribution. So for the log normal distribution, we know what is the value or what is the distribution or the marginal distribution of it. X2, this is for type 1 largest value. Already the distribution is given. If you cannot recall, you just go back to the table and put these values. And H3 for this part. So H3. Now if you simplify this and plot them, you will get the JPDF in this form. Now again, this is the JPDF. We also can have the JCDF also. We have already the equation, or we just need to, integrate it 2 times. We will get the JCDF. Now again, we need to check it. How we can check it? We need to get the marginals from this JPDF. So first, let's get the marginal of f of x1 of x1. How we can get it? Just integrate the joint this joint PDF over dx2. Great. So for the first distribution, log normal case, the yellow line here you can see the yellow line of this curve. We are getting it from the marginals of the joint PDF, whichever we are getting from the Morgenstern model. And again, we need to plot this value. We have uh, the parameter of the log normal distribution. We can plot it, the marginals. So now for this model also, we have seen that x1 and x2, that means type 1 smallest and your log normal distributions also, these marginals are consistent with the marginals we are getting from the JPDF of the Morgenstern model. Okay. Okay. So now if we have one case where we have more than 2 random variables, that means the multivariate case. So for the multivariate case, again, they have prescribed the formula, similar kind of formula. There only the correlation between these two are there. Now here the correlation between up to how many random variables or the how many dimension you have considered up to this you need to consider. Like fx of x, 1 plus first alpha ij, then alpha ijk. So obviously the question will come that alpha ij, okay, I can find it out rho ij by 4 q1 and q2 we have seen. For ijk, how we can find it out? So this formula is given like this. So if we have k dimensions, and again for this multivariate case also, we need to follow the criteria that our alpha ij, that means the scalar multiplier, the value of the scalar multiplier should be less than equals to 1. So using this formula, we can see that alpha 1, 2, 2 up to k, if we need them, so that formula will come like that: rho 1, 2 to k divided by 2 to the power k q1, q2 up to qk. Now let's say, for example, if we have two dimensions, so what will be become alpha 1 2, we will get rho 1 2 divided by 4 q1 q2. Just we have seen the formula and solved for the bivariate case. Okay, so if we have more than two random variables, we can also construct the JPDF and JCDFs using Morgenstern model. But the limitations is again here, we need to check these conditions that my scalar parameter value should be less than 1. That means that will lead to the criteria that there should be a range of correlation coefficient on which this Morgenstern model will. So let's quickly solve one example of that three-dimensional case. If we have that three-dimensional or four-dimensional or multivariate cases. So let's say we have x1, x2, and x3 marginally standard normal with correlation coefficient like rho 1, 2, rho 2, 3, rho 1, 3 is given like 0 0.3. And rho 1, 2, 3 is also given 0.05. Find out the distribution by Morgenstern model. So x1, x2, x3 all normal. Normal are fall under group 1. The value of q1, q2 and q will be equals to 0.282, right? So for alpha 1 2, alpha 2 3 and alpha 1 3, this will be this value. Now for alpha 1 2 3, we have seen the equation that rho 1 2 3 divided by minus 2 to the power k. So here k will be 3 because we have three random variables, so dimension is 3, divided by q1, q2, q3. All values are known. Now when we know these values, just use this equation and complete the PDF. Clear? So by this way, by this process, we can actually develop, or we can actually get the multivariate or bivariate distributions using Morgenstern model. Clear? So let's quickly go through MATLAB and plot these two, like how we get this. Then we will go to another model. So now if you have any questions, you can ask me. So let's quickly, plot these things, like how we are getting this. These are very simple, like you just need to integrate some values over some domain. This is the main task we need to perform. Then we will come back and we will see another model we call Nataf model. Okay. So let's quickly go to that MATLAB window. So just for a second. Okay, is my screen visible? uh Actually the paper is
Yes.
displaying, right? Yeah, so this paper I'm talking about, Bob. So here all these things whatever I have discussed, like what is the PDF form, what is the CDF form, what is the PDF form, and the tables, whatever, directly we have taken it from this paper. So this title lights multivariate distributions with prescribed model. So here they have prescribed that Morgenstern as well as Nataf model. So Morgenstern first, then they discuss the Nataf model here. So we will also discuss the Nataf model. So first let's solve the problem in MATLAB first, whatever we have seen. So the first problem, right, Morgenstern. What is the problem statement? Let's quickly go through it first. So we have two random variables x1 and x2 which are marginally normal and the parameters are given. Also we have calculated the alpha. So our task is to plot this JPDF, get the marginals of x1 and x2, verify them with the actual marginals. Clear? That is our problem statement. So let's quickly check it. So first here, I hope the MATLAB window is visible, right? MATLAB editor. Okay. So
Yes.
first we need to define some array for x and y. So let's say we start with a 100 number of samples. Okay. Now row 1 2 we have that value is given -2. If you know go back to this, the row 1 2 is given as 0 point minus 0.2. Okay, I have taken it from there. Mu1 for the first random variable, mu1 sigma 1 given. Now q1 already we have found it out from the table 1, 0.82. Now I am constructing the x array. So it's like 0.1 to 10 and number of that random samples what we need, or you can increase or decrease this array also as per your convenience. Now mu2, the second variable, follows exponential distribution which has only one parameter, lambda, and recall lambda is nothing but 1 by mu, right? And the variance 1 by mu square. Directly we can find it out. First class we have seen this. Now for the q2 also we have create an array on which we need to plot the distribution. Now alpha, the formula of alpha, row 1 2 divided by 4 q1 and q2. Okay, all the parameters and values whatever we have initially in our hand, we just feed it. Now first what we need to construct the marginals, actual marginals based on these parameters. So first for fx of x1 it's the normal, so normal pdf. If that capital X, that means the CDF, the normal CDF, we have constructed based on mu1 and sigma 1, the actual values which are provided. Okay, because we need them when we calculate the JPDF. Also we will need them to verify the marginals getting from the JPDF. So here for the first random variable f x1 and f of x1, that means CDF and PDF both we are getting, and for the second variable also we construct it. Clear up to this? Now our task is to find out the joint PDF or the bivariate PDF, because here we have only two random variables, so we can get it. So like what was the formula? Just put it here. F x1 of x2 is equals to f x1 f x2 multiplied by 1 plus alpha 1 minus 2 f of x1 1 minus 2 f of x2. Whatever we have just seen here, like this formula, f of x1 f of x2 and this all, right? So we have feed all this thing here. Now we have here, we already construct the JPDF using Morgenstern model. Now how to plot them, rest I will see. Now the thing is how to plot them. So first, if I want to plot this JPDF, we need to create a surface of x1 and x2, and over this we need to make a mesh plot. So let's see we are getting this or not. Okay, then I will go how we can create it. First let's close them and go one by one. So first let's check we are getting the JCDF or not. So this is the joint CDF using the marginals whatever we are provided, and using the Morgenstern model. So yes, we have getting the same PDF whatever we have seen in the PPT, right? Here you can see this one, right? This one. So this one already we are getting using the Morgenstern model. Now, okay, we are getting it whatever. Now to check it, like is my that JPDF is uh, consistent with the marginals based on which I have created it. So first let's see, first let's plot the JCDF also. So let's plot the JCDF. Then we will go to for the checking part. So up to this, what we have done, we plot the joint PDF using marginals. Now how we can get the CDF? We have the formula of CDF. So here I just integrate it two times the PDF, I get the CDF. Okay, and similarly, if you plot it over that x and y domain here, similarly you need to create a mesh, or you create two dimension on which you need to create a mesh plot, because it's a three-dimensional plot. So you need to create some grid or mesh, then on which you need to plot it. Okay, so let's see what will be the JCDF. So this will give the JCDF. And look at the value of CDF. We already seen that the last value of CDF should be equals to 1. So it also converge up to some 999 value. Okay, nearly equals to 1. So it's okay. Now we need to check whether the marginals we are getting from this JPDF and JCDF, whatever we have constructed, they are actually consistent with the actual marginals or not. So actual marginals we have constructed here, so we can directly call them from here. Now we need to construct the marginals from the JPDF, whatever we have constructed using the Morgenstern model. So here we can see the marginals of x1. Marginal of x1, how we can get it? You need to integrate that function over the another domain x2. So here that integration part is done, and the marginal of x2 here, again the integration over x1 domain is done. Now if we plot these two values here, like sum1 and sum2, with the actual marginals whatever we are getting from the values provided, so we can check and verify. Okay, if our plots are consistent, then okay. If not, then we need to verify like where we did the mistakes. So now if we run it, first for the first variable, we can see on your screen that the blue line, the fx of x1, the blue one, what is this? This is the actual marginal based on the parameter whatever is given. Now what is that blue line means? That is, I have integrated the JPDF whatever I get from the Morgenstern model, this curve like value, and integrate over dx2 domain, I get this curve. Clear? That means these two plots are consistent. That means we can say okay, the model is fair enough. Now for the second variable also, look at this exponential. Again the blue line plot based on the parameters whatever given, that means the actual marginals, and the yellow line whatever I have plotted, this is the integral form of the JPDF over x1 domain. Clear? That means okay, these models are consistent with the prescribed marginals, but there are some limitations, like we need to have some range of correlation coefficient on which this model will act. So similarly, we can go with the second problem too. Like in second problem, what we have two different distributions, log normal and the type 1 smallest. So for these two also we can plot similarly. Rho 1 2 is given, mu and sigma given. Okay, q we have found out q1 q2. Similarly we have form x array, y array, or x1 array, y1 array, then alpha. First, simultaneously, we have created the marginals, actual marginals, based on the parameters whatever given. Then we have constructed, or I have constructed this uh, joint PDF using the Morgenstern model, and 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 similarly the marginals we are getting from here, same code, same type of code, and if we run it, we will get the final results. So let's see. Yeah, so that is the J. What is this? What is this? This is the joint CDF of the two random variables, log normal and exponential case. Again, this is the joint PDF of these two random variables, and these are the checks. You can see this one is for x1 random variables, x1 marginals. These are also well within the prescribed one, and the second one is also well within the prescribed one. This is overlapped one. That means okay, for this problem we can use this multivariate PDFs. If we have any problem as per this given data and as per these given values, we can use them because these are already verified. Okay, now we can go with the models. So I hope that you have some glimpse of what the Morgenstern model do and how we can get the bivariate or multivariate PDFs and CDFs or the distributions in particular form, so we can have the Morgenstern model. Clear? Like these models, if you need in any research problem, if you need this kind of model to use, then only you need to work with these models. Otherwise, not necessarily in everywhere in reliability or everywhere in statistics you are going to use them. Okay, when you need it? Okay, when? Because in civil engineering applications, like we have minimum minimum we have limitations on data, like we cannot have the privilege to have the big number of data or the samples. So very often what we need to do, we need to prescribe some marginals over some limited data, and for these cases to reconstruct and re-verify the correlation between them, we need some multivariate model. So for these cases we may need this kind of models. Okay, now let's quickly go through another model that we call Nataf. Again, this Nataf model is also, they have
Excuse me.
prescribed in the, yeah, Abul.
Yeah, I'm really sorry. I just lost my focus. You told something about civil engineering. Like we do not have the privilege of having a lot of data. So
Yeah,
can you repeat that?
yeah. For them, like for example, you are testing concrete cubes. Okay, so you cannot test 500, 600 samples, can you? So
True, true.
yeah, so you can test hardly like six samples, 18 or 6 multiplied by 6, 36 or some more. So based
Hmm.
on that limited data, you can prescribe some marginal. Okay, it will follow log normal distribution or it will follow some other distribution. Okay,
Uh-huh.
so but when we do the precise reliability analysis, we cannot find out the actual correlation between these values. So for this type of problems, when we encounter, we need to have these bivariate models and which are actually consistent with the prescribed marginal, so that we can we can verify our final results. Okay, whatever we are getting from this statistics of samples, that will be well within the prescribed values. So if I suggest, if you go through this paper, they have some introductory portion why we need them and these are given. But thing is thing is like most of the cases when we have the limited access of data, we need to prescribe some distribution, right? Otherwise we cannot perform the probability and reliability analysis, all these things. Now
Yes.
when we prescribed it, this is the initial guess. Okay, this will be this. We cannot or we don't know what will be the correlation, what is the exact correlation. So if we have some bivariate distribution or multivariate distribution, for these cases this will be more helpful. Clear?
Okay. Okay.
Now let's see another kind of distributions, another kind of model which will give the same kind of end product, and like joint distributions or multivariate distributions in uh, uh, multivariate distributions more precisely. So we call Nataf model. Now in Morgenstern model, sorry, what we have seen that there there are some limitations regarding rho. So here we will see what that Nataf model will do. So in Nataf model, we will get the bivariate PDF or multivariate PDF using, here the concept behind the Nataf transformation is like one-to-one mapping between the original space and standard normal space. The logic behind it, or logic behind developing this model was one-to-one mapping to original space to standard normal space, and to find out the correlation matrix between normal and standard normal space. If we can do this, or we can have the joint distributions in the form of this. So as per the Nataf model, the joint PDF between two random variables x1 and x2. So for them, we can have the joint PDF in this form. We need to multiply the marginal of these distributions multiplied by this. This part actually describes the one-to-one mapping on standard normal space. Like the this one phi of n z c dash. This is nothing but n-dimensional PDF of standard normal distributions. Okay, n-dimensional standard normal distribution. And we have seen that for the normal distribution we can easily get the joint PDF or CDFs using marginals. We have the liberty with the normal distribution. So if we have the liberty with the normal distributions, obviously we can have with the standard normal distributions. So, and these are the phi of z1, phi of z2, up to phi of zn. These are the marginals in the standard normal space. So if we have x1, we can find out the corresponding z1. Like phi of z1 is equals to f of x1. We have solved so many problems in first order reliability method in normal and standard normal space, so we know it. So our task here is to find out this C matrix. That means the covariance matrix in the standard normal space. If we know the covariance matrix in actual space, all the time it will not be the case when we will have the same covariance matrix on the standard normal space. So our first goal is to find out this C matrix. Once we have this C matrix, this part of this equation, if we can solve it, we can easily get the joint PDF or joint CDF using Nataf model. Now let's see how we can find out this. So again, they have established this using the relation of the correlation coefficient. So correlation coefficient between the two random variable, they have integrated, and after simplifying that, if we can solve this equation, look, rho ij is equals to, we have rho ij prime. Rho ij, the correlation of the random variables on the actual space, rho ij dash after getting on the standard normal space. Now this equation we can solve by numerically, or they have prescribed some closed form solution, or, or the closed form relation between rho ij and rho ij prime for different kind of random variables, so that we can skip the numerical solution part and directly get the values. So recall that this is nothing but the n dimensional JPDF in standard normal space. So this relation already we have know that this is nothing but 1 by root over of pi square 1 minus rho ij prime square exp 1 by 2 1 minus rho ij prime z1 square minus 2 rho ij prime z1 z2 z2 square, and divided by this is nothing but phi of x1 and phi of x2, and we know phi of x1 and x2 we can have them in the z space also. So this is an very useful equation which tells you the n-dimensional JPDF of the standard normal distributions. Okay, now the thing is, the problem get not solved, like we need to find out the relation between rho and rho ij prime, because initially when we start working with the marginals we will have the correlation between two in normal space. So they have prescribed, like if you have a bunch of random variables, first they have categorized them, and based on these values they have you know given the equation of rho ij prime and rho ij. Okay, so they have told that rho ij prime is nothing but f time rho ij. Now we need to find out the f is nothing but a function of that correlation coefficient and the marginals, whatever we are considered for our joint PDF or joint CDF. So first they have categorized this into 5 groups or 5 categories based on the nature of the random variables. So first, f will be constant for xi normal, xj belong to group 1. Now group 1, group 2 we have already seen for the Morgenstern model. Here these are the group 1 variables and these are the group 2 variables, right? So now for these 5 categories, they have tabulated the values of f or the relation of f. So we can directly get these values from this paper. Now we will see one by one, like f will be constant for x1 normal, xj belongs to group 1. F equals to f of del j, that means is a function of coefficient of variation if x is normal and xj belongs to group 2. And similarly, this will be a function of rho if xi and xj belongs to group 1. This is a function of rho and del if xi belong to group 1, xj belong to group 2 and all. So first we will see these 5 categories. Okay. So first category, like here in this paper they have tabulated these categories. Here, this is the paper, I will share with you, no problem. So first category, what we have said, that f is constant for xj belong to group 1 and xi is normal. So if this is the case, and if we have the xj values, that means xi is normal. So what will be the other distribution we are considering? If they are falls under this, so we can get the value of f. And once we have f, we can find out that rho ij is equals to f time rho ij prime, right? This was the equation, or this was the relation given by them. Rho ij prime, sorry, rho ij prime is equals to rho ij into f. Rho ij prime is equals to rho ij into f. So if once we have the f value, we can find out the rho ij prime value and we can construct the JPDF. Now for the category 2, this is a function of coefficient of variation if your xj belong to group 2 and xi is normal. So if for our problem this combination occurs, then we can find out the f value from here. Look, the f value is, we can get it using the del, because we have seen that for category 2 that f is a function of del. So here if we have log normal distribution, the f value we can get using this expression. If we have gamma distribution, using this expression, and all these things. So del, first we can find out the del value. Del is nothing but sigma by mu, right? Coefficient of variation. Right. Now if we have category 3, where f is a function of rho ij, that means both your xi and xj belongs to group 1. So for this case, the f value we will get it from these expressions, and these expressions are very handy. We will solve some problems so we can see it. So category 3. Now move to category 4. Here the that f value is a function of rho ij and del. That means this condition will occur when xj belong to group 1, sorry, xi belong to group 1 and xj belong to group 2. And group 1 and group 2, what that group? That means we have already categorized this group 1 and group 2. First group, that means we can reduce them to their standard forms. And group 2, first categorization of Morgenstern model, just recall that groups. Now for the group 5 also, we have similar kind of expressions. So all these tables, all these values are given in this paper. This all we have collected it from there. So now the question is, we have seen that if we have, if we know the random variables, nature of the random variables, so we can find out the rho ij prime value. This is nothing but f into rho ij. If we can find it out based on the nature of the random variable, we can find it out. Okay. Now once we have find all these values like f or the rho ij prime, we can construct the JCDF using the Nataf model. Now the thing is, like in Morgenstern model, we have seen that there was limitations regarding the rho 1 to or the rho. That means we cannot apply this Morgenstern model beyond some values of rho. Let's see for the Nataf model, what should be the range of these random variables. So here, let's say x1 and x2, these are marginally normal and uniform. Look, marginally normal and uniform, right? So first we need to find it out what will be the rho ij prime. That means first we need to find it out what will be the value of. Now tell me how you can find out the value of f. So first one is normal, second one is uniform. So you need to check under which category this combination will fall, right? So which category this combination will fall? Normal and uniform. Just
The first one, group
first,
one.
right? The first category. If constant होगा जब xj belongs to group 1 and xi normal. So recall our problem, xi normal and xj. What was the xj? Uniform, right? So what will be the value of f? 1.023. 1.023. So how I can find the value of f, or you can find it out the value of f? Now you understood, right? Now once we have that f value, the rho ij prime should be less than equals to 1 for the Nataf model. Now, if we put these values, rho ij prime less than equals to 1, that means rho ij into f less than equals to 1. So, rho ij will be equals to 1 by f. That means rho ij should be less than equals to 0.977. Now, for the same problem, using your Morgenstern model, what was the limiting value of rho? Recall, we just solved this problem, normal and uniform. The value was 0.326, right? We just have solved
Yes.
it. Yeah. So that means we can see that the limitations, whatever we had with the Morgenstern model, now we can say that for the wide range of this, here we can say the range. That means beyond which we cannot use the Morgenstern model to establish the JPDF or JCDF. You establish them, forcefully, your marginals will not match with the actual marginals. Okay, you can do the exercise and check whether these are giving that satisfactory result or not. Okay, so here we have seen that the Nataf model is actually applicable to wider range of rho. That means correlation coefficients between the random variables here. So in that paper, they have calculated for different kind of variables like normal, uniform, normal, exponential, shifted exponential for this, and they have tabulated all the lower and upper bound for the rho. Okay, and we can see that, okay, for a wider range of rows, look at the values like 0.9 to 0.9, 1 to 0.8. We can and most of the engineering applications or engineering problems will fall under this row. So this is very popular and handy method to solve or to get the joint PDF and joint CDFs or bivariate and multivariate distributions. So now let's quickly solve one problem of the Nataf model. Then this model will get more clear, right? So using the Nataf model, recall what is the formula to get the joint PDF? This. You multiply the marginal with the joint PDF of the standard normal distributions divided by the marginals of the standard normal distributions. Now let's see what that example says. If we have x1 and x2 marginally normal with mean 5 and sigma 1.5 and exponential distribution with mean 1 with correlation coefficient minus 0.2. Now, no, there is no relation between Morgenstern and Nataf model because these two models work separately. In Morgenstern model, we have seen that we get that joint PDF and CDF using some scalar factor, which actually tells us about the correlations. Here, we are doing the one-to-one mapping between the standard normal space and actual space. So there is actually no relation between them, between these two. Okay, these are two separate model and they will work separately. Now there are ranges of correlations within which you will get the same kind of PDF and CDF using these two models. Like the same problem. Look at the problem. This is the same problem we have solved using the Morgenstern model. And look, this kind of this was our JCDF. and this was our JPDF and marginals. So same thing, because the correlation coefficient, the value of correlation coefficient same, minus point. Now if we increase that like 0 0.8, 0 0.9, then Morgenstern model will not work, the Nataf model will work. Okay, so look at the same problem. Same problem we have solved using the Morgenstern model, and look at this PDF and CDFs, JPDF and JCDFs. They are actually look same, because the range is within the Morgenstern and Nataf model, so we will get the same values here, this problem, right? So let's solve using the Nataf transformation, and this will give us the confidence, okay, how this model will work. Yeah, so first we have normal distribution and exponential, shifted exponential. So first task is to find out the f. So what will be the value of f? Again, normal and x2 belonging to group 1. That means the value of f will be constant. So first table we will get the value 1.101. From where? Because these tables, if you know these tables, you can feed it into your MATLAB as a function file and call them. So it will identify and directly get the values. Here, look, group 1, that xi is normal and xj is belong to group 1, and we have shifted exponential. For shifted exponential, what is the value of f for this combination? 1.107. So from here we are getting the value. Okay, now once we have f, we can find out the rho ij prime. So rho ij prime will be rho ij into f. The rho ij value is given 0.2 minus 0.2. Now we can construct the JPDF. So I have simplified H1, H2 and H3. Three parts I have divided. Like H1 is for f x1 of x1. What is that? F x1 of x1. This one will be x1. Okay, x1. F x of x1. What is that? What is that, Abdul? F x1 of x1 is the marginal PDF of the normal distribution. Yes or no?
Yeah, fx1 x1, yeah,
Yeah,
marginal PD.
marginal distribution. So look, this one is the PDF of your normal distribution. What is that?
Mhm.
PDF of the exponential
That's-
distribution.
Yeah.
And this part is the first, your upper part, what do we call it? The n dimensional PDF of the standard normal distribution. So this was the actual relation for this. Here you can put the rho ij prime value, and z corresponding x1 to z1, we can find it out through standard normal transformation, and divided by that phi of z1 and phi of z2, and that is nothing but 1 by root 2 pi exponential of half z1. That means these are nothing but the standard normal marginals. Now if we plot this f x1 x2 over a domain, this we will get from the Nataf transformation. Now if we need to check it, we again go back from here, this f x1 x2 given x1 x2, if we integrate it over the domain, another domain, and then we will get it the other value. So dx2 we will get f x1 of x1, and we will plot this, we will get the pink curve over here, and the blue curve. To get the blue marginals, we have the distribution, normal distribution value, normal, where the mean is 5 and standard deviation is 1.5, and if you plot them, you will get these two marginals. And here we can see that the marginals we are getting from the JPDF, and the marginals, actual marginals or the prescribed marginals, are you know overlapping, or closely matches with each other. And for the exponential distribution also, if we plot it, we are getting the same kind of result. So we will go to the MATLAB and we will see are we getting the results or not. So let's quickly solve another problem, then we will go to the MATLAB one. So this problem, here again we have marginally log normal and type 1 smallest value. So marginally log normal and type 1 smallest value. Your task is to find out the f value. So tell me from where we can get the f value. Log normal and type 1 smallest. So that means x1 belong to group 2, log normal belong to group 2, and this x2 belong to group 1. So xi belong to group 2 and xj belong to group 1. For that, what will be the value of f? You need to find it out from the table. So tell me what will be the value. I will show you the table. Yeah. Xi belong to group 1 and xj belongs to group 2. But our case was just remember this. I just forgot it.
Log normal and
Log normal and yeah,
type 1 smallest.
belong to group 2 and group 1. That means x1 xi belongs to group 1, a group 2, and xj belongs to group 1. And we have just remember log normal and type 1 smallest. Right. So xi belong to group 1 and xj belongs to group 2. Can I go with this table? Tell me. Can I go with this table? And if we can, what will be the value from here?
Yeah, the fourth column is type 1, is it?
Yeah, right.
Yeah. Uh,
Exactly. So this one, type 1 smallest and log normal. So here, look at the expression. Here we need to find out the rho and del because the f is a function of rho ij and del both because we have log normal and the type 1 value. So first we need to find it out for the del value. So from there we can get the expression, but we need to simplify them. Here look at this 0.192, 0.001, rho 1 to rho and del. It's a function of rho and del. Rho and del. So rho and del we can easily calculate it. Del, it's nothing but here the coefficient of variation. We can get it using the this given formulas or given parameters, and for the type 1 distribution we can find it out the other values. So rho 1 2 already given. This is 0.25. Delta value will be 0.25. Simplify this, you will get f. Now once we have get f, you can find it out rho ij prime. Rho ij prime will be nothing but rho ij multiplied by f. So this value. Now once we have all these things, we can simplify this equation like this and we can plot this. So this is our expression fx of x1. This is for log normal case. This is nothing but the pdf of marginal log normal of log normal. This is the PDF of type 1 smallest, and H3, this is this part in the standard normal domain. This is the n dimensional PDF of the standard normal domain, and these are the marginals of the variables in the standard normal domain. Great. Now if we plot them, these values, if we plot it, we will get the JPDF like this and JCDF like this. Similarly, like same problem we have solved using that and this, and these are within the range of the correlation coefficient. That's why we are getting the same kind of values. So let's quickly go to the MATLAB and quickly verify whether we are getting the same values or not, and this kind of curves or not, and then we will move forward. So this was the Nataf problem. So here we can see the rho, we can find it out already. We have found it out like 0.2214. Here you can see rho, the rho. Okay, now mu sigma, mu1 and sigma 1, these are the first for the first random variable. Yeah, then for the second random variable, again it's an exponential distribution having one parameter. Now here we are constructing the actual marginals based on the given parameter. So this is the normal PDF, this is the exponential PDF. Again we can have the CDFs also, like in this form. If you want to calculate the CDFs, you can get the CDFs also, but for this problem we don't need the CDFs. We, on the other hand, we need the marginals in the standard normal space, so we need to convert them into standard normal space. So here the calculation of Z1 and Z2 is done, because in the denominator, see, phi of Z1, phi of Z2 was there. So here the calculation of this Z domain is done. Now once these two values we can have, then we can easily calculate the the PDF in standard normal space, like the third part. Here you can see the third part, this part, for this part I have calculated here. Now once we have this, like the third part, the marginals in standard normal domain, the marginals in actual domain, now we can calculate, or we can get the JPDF using the Nataf model. Now once we have this, we can plot the JCDF in original space, and once we have these two, we can get the marginals from the PDFs. So these are the marginal one. Using the PDF we are getting from the Nataf model. Again, these are the marginal 2 of the random variable 2 using the joint distributions we are getting using the Nataf model. Now if we plot them, so we will get what we are getting. Let's see. Yeah. So first, this is the joint PDF using the Nataf model. This is the joint CDF using the Nataf model. Now the thing is, like, are they consistent with the prescribed one? So again, what we need to do, we have the actual marginal of x1 and x2. The actual marginal of x1 was the normal distribution. You can see in your green line, this one, if x1 of x1, mu 5 and sigma something 1.5, we can directly plot over an area of x. Now the pink one is nothing but getting the marginal 1 from this JCDF, JPDF. Now if we integrate this with respect to x1, we will get the fx of x2. If we integrate it over x1 domain, we'll get x2. If we integrate it over x2 domain, we will get x1. So similarly, I have integrated it with x2 domain, I getting the marginal of x1. So marginal of x1, the prescribed one was the normal, and whatever we are getting from this model, they are same, almost same. Now for the second variable also, we can construct the JCDF and JPDF marginals from the JCDF and the actual marginal. So f of x2, this is the actual marginal, whatever we have plotted using the given given parameters, and the pink one is the marginal, we are getting it from the JPDF by integrating it over another domain. So these all things we have checked, cross checked, and we have seen that okay, all models are working. Like here, first what we have done, let's quickly go through it one by one again. So first we have feed all the variables for x1 and x2. We create an array. Now we calculate the PDF of the given, or the marginals of the given distributions using the given parameters. So normal distribution and exponential distribution. Now recall, we also need the marginals to calculate our PDF in standard normal domain. So we need phi of Z1 and phi of Z2. So we need to calculate them also. So here in this part, the calculation of Z1 and Z2 is done. So it's Z1, like it's standard normal space. We just norm inverse command is there. So we can use this norm inverse command using the mu and sigma value. That means the parameter already are given there, and for exponential distribution is also. Now once we have this, we can construct this whole expression of the third part in standard normal domain. Now once we have these three, 1 2 3, we can find out the joint PDF. So here what I have or what this code calculates in this portion or in this section is this value, this value. Now once we have all these values, we just assemble it, and we will get the joint PDF using the Nataf transformation. Like f x of x1, this is the marginal of this, already we have calculated. F x of x2, already we have calculated. And this is the, for the third part of the equations, this is calculated using z1 and z2 plus the upper part, the n dimensional n dimensional PDF, the equation of the n dimensional PDF. You will feed it here, you will get this JPDF. Now if you plot them over x1 and x2, here the plotting is done. Here if you plot them like this third plot, you can see over here. Here, so we have the joint PDF. Just plot it here, you will get the joint PDF. Now again, if you have the joint PDF, you can integrate it over dx2 and dx1, so you will get the marginals. Now we can construct the CDF also. Here the CDF is constructed, this part, joint CDF is constructed. The CDF formula is also given, or from the relation between PDF and CDF you can construct it. What is the relation between PDF and CDF? If we have the multivariate case or simple case, what is the probability density function and the probability distribution function? So PDF is equals to ddx of CDF, right? And CDF is equals to integration of PDF over
PDF.
this domain. So here I have opted for the second one and did it. Now once we have the CDF, we can plot the CDF too. Here in this part, the CDF portion is plotted. Just plot it. This is the CDF, joint CDF. Now we need the marginals. So actual marginals already we have calculated here based on the given parameters. This. Now we need to plot them with the marginals we are getting from the fx of x1 from fx1 x2 of x1 x2. So marginal of x1, here you can see, you just need to integrate over x2 domain. Now for x2, you just need to integrate your fx of that function, fx of x1 and x2 over x1 domain. Now here the plotting things have been done. Right here. This. For the first random variable, we can plot it. So this fx of x1, we are getting it from previous, like given parameters and all these things. And the pink one, I am getting it from integrating the joint PDF over the domain of x2. Similarly, for the second one also, for the second case also, you can find it out, the value. Just run this section, you will get this for the second one. So it's okay. And similarly, for the second problem also, I have checked for the second problem here, Nataf 2, whatever we have seen for log normal and type 1 largest value, this one is also there. So I will upload these codes, you just check it and run it. You will get the same values. Also I have calculated the volume under these curves to check whether it is I am getting 1 or not. So it's like volume is getting 1, but sometimes using the marginals we are close to 1 but not exactly 1, like 0 0.999, 0 0.98 and all these things. Okay, so now up to this point we know about the Morgenstern and Nataf model. What they do, they convert, or they will give us the bivariate or multivariate distributions based on the marginals, and we have seen the models are consistent with the given marginals. Clear? So let's
Yes.
quickly solve some problems regarding your assignments, then we will go to that Rosenblatt transformation. Okay. And Rosenblatt actually different kind of transformation. It will not give you that JPDF or JCDF. What Rosenblatt transformation does, actually it convert your X space into Z space directly based on some conditional probability. We'll discuss in a minute. Okay. So first let's quickly solve some problems. Then we will come back into the Rosenblatt transformation. Okay. So it's the first question. Let's solve it. Simultaneously. You and me simultaneously. So let's say x1 and x2 marginally normal and exponentially distributed. We have just solved it, right? Q1 is given, Q2 is given. Find out the maximum limit of correlation coefficient between two random variables. Okay, can we find it out? Now the question is actually incomplete, that you need to specify that you need to use Morgenstern model. Okay, Morgenstern model, because if the Nataf model, you will get different kind of values. Although the Q1 and Q2 are related to the Morgenstern model directly, so we can say it, but still using Morgenstern model. Now we have Q1, Q2. Now recall what was the limitation for the Morgenstern model, that your alpha value should be less than equals to 1. And what we have the relation, alpha is equals to nothing but rho 1 2 divided by 4 Q1 Q2. 4 for the 2. If we have multivariate, minus 2 to the power k was there. So that should be less than equals to 1. Rho 1 2 value. We know the rho 1 2 value. What is the rho 1 2 value? We need to find it out. Okay. So rho 1 2 should be less than equals to 4 Q1 Q2. Q1 Q2 value you know. So what will be the range of this? 2.282. Clear? Now, second question. X1 and X2 are marginally normal and log normal distribution. The coefficient of variation is given 3. Find out the value of f. That means you need to use the Nataf model. So f value you need to decide. You have two kind of distribution. One is normal and another is log normal. So what will be the value of f? That means your xi is normal, but xj falls under category 2. That means your f value will be the function of the coefficient of variation, del, right? So just go to that table, and these all tables are given in this paper, that paper, whatever I have showed to you. So while solving the problem, you just need to carefully check the table, or you can do the numerical integrations. But I prefer this. These expressions are very handy. You don't go with this. Xj is normal and this xi is normal and xj fall to group 2. So this will be the expression to find out the value of f. Now del, coefficient of variation already given. So you just need to put all these values and simplify the equation. Yeah. So this one is the value expression for it. Del, coefficient of variation already given 0.3. And if you simplify this expression, I hope you will get these values. Just cross check it, you are getting it or not. If you are having if you have any calculator, just cross check it.
The
Yeah.
same.
Okay, now let's move to the next question. Here what we have three random variables and all are marginally standard normal. The correlation coefficient rho 1 2 rho 2 3 rho 1 3 is given, and rho 1 2 3 is also given. Okay, q1 q2 q3 is also given. Calculate the alpha 1 2 3. It's very simple. That alpha, the what was the relation between alpha 1 2 3 for multivariate case? Rho 1 2 3 divided by minus 2 to the power k. That means here 2 to the power 3 q1 q2 q3. So you have all the values, put it here, and you are getting the value or not, just check it.
Same.
Okay. Now let's move to next question. X1 and x2 marginally normal and exponential. We have solved it. Correlation coefficient rho 1 2 is given. What will be the value of alpha used to calculate the joint distribution by the Morgenstern model? Consider Q1 and Q2 is this. Okay, that means Q1 Q2 already given. That means they have already simplified your life, or make your life simple. You don't need to go to that table and you need to look for the values. So x1 is marginally normal and x2 is exponential. So q1 and q2, from where we can get it? Group 1. Both fall under group 1. So q1 value, or already they have given the value of q1 and q2. So alpha is nothing but rho 1 2 divided by 4 q1 q2. So this value we are getting same value.
Yes.
Okay. Now let's solve this problem. Let the variable x and y are marginally normal and exponential respectively with correlation coefficient 0.2. The joint distribution by Morgenstern model, Morgenstern एक साथ में होगा, model can be expressed as this. So where h1 is equals to f of x, x and f y of y. Find the value of h1. Okay, great. So it's nothing, you just need to multiply these two marginals. So first one, x1 is marginally normal. So what is the marginal distribution of normal distribution? Is nothing but 1 by sigma x under root of twice pi exp half x minus mu x by sigma x. For the exponential distribution, f y of y is nothing but lambda I to the power minus lambda y. Now the lambda value is given as 1. Mu is given 1, that means lambda is equals to 1 by mu. So if mu is 1, so lambda will be 1. So this will be your marginal of exponential distribution. Now this one is the joint PDF using the Morgenstern model. So if we simplify it, h1 and h2, what will be the h1 value? This one will be 1 by this means they have expressed is like h1 into h2. That means h1 is complete this part. Yes or no? So if we need that h, that means you need to multiply fx of x1 multiplied by fy of y1. That means the marginal of normal distribution, marginal of exponential distribution. Now just simplify this equation, you will get this expression. Clear? Well, I hope we have one more problem left. Okay, no, we have problems. So previous problem, clear, Abdul, Bob,
I
clear?
lost my connection.
Okay,
Uh,
okay, no issues.
how
Like
did we
Yeah.
how did we choose alpha 1 minus 2 f of x? Is it mentioned somewhere? Did
this,
I miss something? Like we chose h1 multiplied to h, right?
yeah, h1 multiplied by h2, the whole thing, this whole thing.
Uh, how do we choose what is h1 and what is h2? How to
Yeah,
bifurcate it?
yeah, yeah, yeah. Here, that h1 is like already they have mentioned like h1 should be f of x1 multiplied by f of x2. What did he given?
Okay, okay, sorry. Fine, fine.
So just you need to multiply these two marginal PDFs, this one for normal, this one for exponential, and simplify the equation, you will get the result. Okay. Yeah, your question is valid.
Fine.
Like we have 1, 2, 3, 4 terms. So whom we consider h1 and whom we consider h2. But here they
Thank you.
have mentioned that h1 is the first whole this part. That means f x of x and f y of y. For the sake of this problem. Okay. Clear? Okay.
Yeah, it's clear.
So here we have another example like x1 and x2 marginally normal and exponential with the given parameters. Correlation coefficient is given, f is given. Find the expression of phi to uc dash, that upper part, that of the last expression. So this is the expression for it. Here the f value rho 1 to value is given. So from there you can find it out rho 1 to dash value. Once you have the rho 1 to dash value, you just put or substitute these values in this equation and simplify it. You will get this expression. And this is the final result for your expressions. Clear? Okay. Now one more problem. This problem actually from the Rosenblatt transformation. So we haven't go through the Rosenblatt transformation yet, but how you can tackle this problem, I will say, then we will go to the Rosenblatt transformation. So like in Rosenblatt transformation, there is a relation between your normal domain and standard normal domain, and this through the Jacobian we can find it out. So if we have the Jacobian, so we can construct a relation through Rosenblatt transformation like dg by dz1 dg by dz2, these are the gradients in the standard normal domain, is actually related through Jacobian inverse by the gradients in the actual domain. So you have the Jacobian here. Now if you do the inverse, you can get this. Now from where I can get these values, I have g of x, I can differentiate with respect to x1, I can differentiate with respect to x2, and if I do, I will get these values. Okay, now multiply with that, you will get this dg by dz1 dg by dz2. Okay, now they have asked the find out the value of alpha 1. Alpha 1, that means the direction cosine. Alpha 1 is here the direction cosine. So recall the definition of direction cosine. Alpha 1 is equals to nothing but minus del g by del z1 by Euclidean norm of g. Yes or no? We have solved so many problems when we use the Rackwood's algorithm, and so once we have this, we can find out the Euclidean norm of g is nothing but under root of this square plus this square. So norm of the gradient vector. Now once we have this, we can find out the alpha. Alpha is equals to minus dg by dz1. This means this value dg by dz1, this divided by Euclidean norm of this. Alpha 2, can we find it out the alpha 2 value? Yes, that will be dg by dz2 divided by Euclidean norm of g minus. Okay, clear how we are getting these values? So this expression actually uh, comes from the Rosenblatt transformation. So quickly we will go through the Rosenblatt transformation now, then we will close our discussion. So this problem is clear how we are getting the alpha value? Yes or no? I think this type of problem is there
Yes.
in your assignments, so you can solve it. Okay, so I hope your all kind of assignments have been solved, right? Now we can go through the Rosenblatt model and discuss what actually the Rosenblatt model do and how we can use them or use it to our reliability problem. Okay, or we can discuss it on the next class too, but still, okay, let's, we have 10 minutes, so we can discuss it. Okay, so that two models like Nataf and Morgenstern, they will give us the multivariate distributions. Now the Rosenblatt transformation, what it will give, it will convert our x space to directly z space through some intermediate step, or we can say based on some conditional probabilities. Now how this transformation looks like and how the algorithm will work, I will just quickly describe. So first, if we have a normal domain where the random variables are given as like x1 x2 to xk, so first we can convert it into an uniform domain u. So this transformation, through this transformation, u is equal to t into x, and it's a nonlinear transformation, and this is based on some conditions like first u1, when we find it out u1, that means the probability of getting x1 less than or so x1, we will get the cdf of x1. Then on the next part, when we calculate the u2 value, then the first value we are getting it from fx of x1, that will be condition. That means we are getting the intermediate steps. Okay, so once we have that u1 and u2, what that u space, it's the uniform domain, from the actual domain to uniform domain. Now from the uniform domain to the standard normal domain, we can again convert like these formulas. Like if we have ui and we need to convert it into zi, that means into the standard normal domain, use this as a condition. Like phi of z1 is nothing but fx of x1, but phi of z2 will be fx of x2 condition over x1. That means whatever we are getting from the previous steps, we have to use it. Now once similarly we will go up to zk. Once we have z values, once we have phi of z values, we can get the z1 values, phi inverse of this, phi inverse of again this, we can get the directly z space from the x space through an intermediate steps where the conditions are applied. So what Rosenblatt model actually do? So it will convert your X space into directly Z space. Now, how we can use this model for our reliability problem? So recall, like when we are solving the Hasse-Farlin reliability index, so we have first we have a limit state in X space, then we convert it into Z space, and as per the definition of Hasse-Farlin reliability index, it was the shortest distance of the limit state in the standard normal domain from the origin. So we need to find it out the shortest distance, and we actually solve this problem using Lagrange optimization technique and using Hasse-Farlin reliability index using the Rackwitz algorithm. Now here the X space and Z space actually connected through the Jacobian. Like we can write g of x is equals to Jacobian multiplied by g of z, and where these Jacobians are nothing but that jij will get dz by dxj. That means we have our limit state in standard normal space. We can we can differentiate with respect to this. So here from here the relation is established. Like if we have the gradient in x domain, these are related via Jacobian multiplied by your z domain, x domain to z domain. Now from z domain to x domain, just j inverse of these values. Precisely we what we have done in the previous problem. So now here, if we can find out the Jacobians, and the expression for Jacobians are already given here, del z by del xi and del g by del xi, and if you put it and simplify it, you will get this relation. Now, if we have the Jacobian, we can directly find out the direction cosines. Now, once we have the direction cosines, we can use this as a reference point to find out the Z1 and Z2. And once we have the Z1 and Z2, we can further proceed for the next iteration. That means we don't need to, solve the beta in a numerical form, and all these things we can skip it. So in our first order reliability problem using the Rackwitz algorithm, we can actually use the Rosenblatt transformation model. So here the problem of the Rosenblatt transformation model, one problem I have added, you can go through it, we can solve it using the Rosenblatt model. So today we have running out of time, but we will have time on like 7th or 8th or 9th week when we are have time. So we will discuss that Rosenblatt model and how we can implement it in our form first order reliability method problem. We will discuss them. So today up to this we will conclude it here. If you have any questions and doubts, you can ask me. Or this part I think will not required for your assignments, but still we will discuss the concept. I hope you understood that what that model does, and if you go through the videos of Professor Onassis Chakraborty, he will explain these things, so you can get it from there. But still we will solve this problem or one problem using Rosenblatt transformation, how these values are coming, how this conditional probability work, and how we can solve this problem uh, using these transformations. Okay, so today what we have done, actually we go through that two models, Morgenstern and Nataf, how to construct JPDF and JCDF using that two models, and we have seen, okay, we can use that models because these models are consistent with the prescribed marginals. And also we have seen that we verify these problems using MATLAB. So if you have any doubts and questions, you can ask me, or else we can end our session. So Abdul.
Yeah, I have a question,
Yeah.
but that is not related to our topic. It is of next week, MCS. Can I ask it?
MCS, okay, you can ask on the next session, or you can just message me. Monte Carlo
I'm actually
simulation.
stuck right now. That's right.
Okay, so you
I'm
can
stuck.
mail me or message me where you got stuck. I will explain it. Like I need that PPT of where you got stuck, that I can directly point it out. Like it's a simulation based technique, so where particularly which state or
No,
which.
basically, I'm unable to distinguish what are the number of simulations I'm required to have for, say, reliability index of 3. I have a problem which has a reliability index of 3.
Yeah.
So how many number of simulations should I go with? Should it be 3 lakh, 5 lakh, 10 lakh? That is the issue.
Okay.
I found different formulas.
Yeah,
I
yeah,
mean,
yeah,
from
yeah. There are formulas like how many number of simulations required to get the convergence. Like,
yeah,
yeah, it's in
like
process.
Arunasi Chakrabarti sir, he was what he does is he multiplies it with a factor called k, and he calls it as a confidence interval.
Okay,
I did not find the same in Collins, and I have some books, and they did not mention that.
okay.
So if I use Arunasi Chakrabarti sir's method,
Hmm.
then my simulations would turn from 3 lakh to 10 lakh, and that
Yeah.
would be trouble for.
Actually, 10 lakh, actually, for my view, is the 10 lakh is the standard numbers. So if we go up to this 10 lakh, then most of the problem will convert. So we will see that particularly this problem you just pointed out how many number of simulations we required. So we will focus on it. Okay, and I will see
Okay.
what SAR has done, and I will get back to you like how many
Oh,
simulation actually required to done. Like 10 lakh, we generally use 10 lakh. Okay,
yeah.
so 10 to the power 6, we just in value 10 to the power 6, and yeah,
Yeah, I'm supposed to do a lot of simulations then. I have
yeah,
some
yeah,
15
yeah,
or
yeah.
20
Actually,
points.
that part you will
That
need
would,
in your research.
yeah.
Okay, I will get back to you. Like how many simulation precisely, what is the relation to find out this, and what
Mhm.
was the values for it. Like generally we consider 10 lakh values. Like if you go with 10 lakh values, you will get the convergence, or you will get the nearest possible result. Okay.
Okay,
Okay,
fine,
so I will explain these things. No problem. Okay,
fine.
so precisely I need to find it out that code so that we can check also that if we change the number of variables and number of samples, so how it will change. Like 10 lakhs is good, but yeah, that there is some formula, and based on that how Sar has constructed, I need to go through it once. Then I can say it to you.
Okay, thank you. Thanks a lot.
Abdul, where are you doing your TO work? From where?
IIT Hyderabad.
Hyderabad itself.
Yeah, Hyderabad itself.
Okay, so is there any facility for in-house TA?
CRTA. Can you please explain some? What is
Like,
that?
like, like, like for the NPTEL, you are also the Prime Minister Research Fellow, right? PMR.
Yeah,
So you
yeah.
need to complete the 50 hours of TA works one where you are.
Ah, true, true, true. I'm doing it from NIT Srinagar,
Okay, okay, okay,
a team over there.
okay, 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 okay.
Ah,
Like me doing this one of the
yeah, I
this
may
thing.
be assisting you next year.
Yeah, yeah, I need to.
Yeah,
One you
I would
can
love.
do from here, and one like nearest college. Like I go to the Assam Engineering College, and I used to teach there like for this semester solid mechanics. So they have given me that solid mechanics.
Okay,
So
okay.
these things. Okay. Okay. But now the simulation based technique, this actually will required for the research purpose. What you are using, like this is actually, and we will ensure the convergence. How many number of samples we need it. This
Mhm.
is the big dilemma. That's why we
True.
go up to 10 to the power 6. That means 10 lakh samples. Go with 10 lakh samples, but it will cost computationally more.
A lot, a lot, a
Huh.
lot.
A lot. You need a high-end computer or the processor to run it within a single click. Like we will solve. Okay, no problem, no issue. But let me first, yeah, I have understood your problem. So to get back to you precisely, so I just go through it and I will tell you.
Thank you. Thank you.
Okay,
I may not be. I may not be able to attend this Sunday's class. I will be going to US for 10 days.
okay, okay.
I would watch the YouTube videos rather and contact you through emails.
Yeah, 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 no problem. So you have any conference or any workshop type?
I actually, it's a visiting scholar thing.
Oh, okay.
Visiting
Great, great, great.
scholar of
Great.
university.
No issue. Just you contact via mail or just watch that YouTube video.
Or I'll WhatsApp you. I have your number.
Yeah,
Thank you for sharing.
you can.
Oh,
Okay. So thank you, Bob. You have any questions, or we can close it.
It's fine. I just have to go through
You
the
just go through this
and
problem.
the pen and paper. Yes, the pen and paper is fine, but the MATLAB I was seeing stars.
Yeah, actually,
So
Bob, this course is like incomplete without MATLAB. You are feeling like that when we are solve that form problem and iso-probabilistic transformation. We will solve some problem and precisely that simulation based technique MCS. But that Abdul just talked few minutes back. So you need MATLAB actually. You need to install it and you need
so
to
so,
handy with it or
so
habituated with it.
I've installed it and I'm learning the basics how to. the language.
Okay,
Okay.
this
The
basic
type
language you can get it from anywhere. What I subtle like you can get it from their basic database also. So the basic language, we don't
yeah.
remember the basic language. Just remember the code. How can we code it? You just think of it and do it. That's how the MATLAB will work. You, if you want to, understand all of the basic of the language, then it will be time consuming, and you cannot remember all these things. Okay, I told you I will share one book. I totally forget. I will share it with you today or tomorrow. Okay. But
Okay.
you
Okay.
need to
That's fine.
practice it.
So
Whatever you are coding, just do some coding. You will get the understand the language. Like just plot sine curve, this plot, this array, this codes, plot it and check whether you just play with the environment and play with the variables or the editor, MATLAB editor. Then you will get to know. Okay.
yeah, I've started. So I'll contact you for any help if
Yeah.
you need be.
Okay. Okay. Then thank you.
Okay. All right.
We will meet on the
Thank you very much.
next week. Thank you.
Next week, unfortunately, I'll be traveling. Like I'll do this traveling, so I may have to watch the YouTube
Okay,
video.
so for next week, Abdul and you both will be absent. Okay, no
But
problem.
I will check wherever possible. If even I can join with phone, I'll try.
Okay, no issue, no issue. But
All right.
I will try to record it with time and upload it with time. Okay, no problem. Okay, thank you.
All right. All right. Thank you very much.